In this video we will discuss about mutual induction. In last video already you got the concept of self-induction. So in self-induction what we saw that there was a coil, and through that coil when current passes, then around the coil or some magnetic flux gets linked with the coil. Okay, and due to that due to change in magnetic flux we get some induced EMF in the coil. So that process is the self-induction. But in mutual induction we have two coils. Two coils we are considering. One is this one. This is one coil. Okay, and the other one is this one. Here I have written P and S. So P means the primary, S means the secondary. Now see, there is a power source which is connected with the primary. So primary is the coil through or with which the power source is connected, and secondary no power source is connected, but yes, there is a galvanometer which will detect the presence of current in this coil. Okay, now here in mutual induction the phenomenon I have written that it is a phenomenon of inducing EMF in a closed coil due to change in current with time in the nearby coil. That means here current is flowing through this coil, primary, right? Now as a result what happens, suppose this primary coil, it has become or it has got some magnetic property. So as a result what will happen, suppose this has become the north pole, this has become the south pole. So from north pole some field lines will come and it will go in through the secondary like this. Okay, so many field lines will come from this north pole and it will pass through the secondary. So when there was no current, right, through secondary there were no field or no flux linked with the secondary. As the current develops in primary, through secondary we are getting some field lines. So that means there is a change in magnetic flux through the secondary. Through primary also there will be change in magnetic flux, but that will be the self-induction concept, right? In self-induction what we said, that current flowing through one coil and the flux is linked with the same coil. So here we are not focusing on primary. Current is flowing through primary, but we are focusing in secondary. That means flux is changing with the secondary. So if flux changes in the secondary there will be a induced EMF or induced current which will be detected by the galvanometer. Okay, so this phenomenon is called mutual induction. Now in mutual induction, suppose phi s is the flux linked with the secondary and IP is the current flowing through the primary. So this flux phi s, it is directly proportional to IP. Okay, so if you remove this proportionality sign, by some equal sign there should be some constant m. In previous cases the concept was the constant was L, coefficient of mutual self induction, but in this case it is m, and there is a coefficient of mutual induction or mutual inductance. Okay, now this m, this will be the coefficient of which coil? Since current is flowing through the primary, it will be the coefficient of mutual induction of the primary. Okay, now the same way here the unit of m is Henry, just like L. Now see here, when IP is 1, this IP is 1, then m and phi s are same, no? M is equal to phi s. So from this we can define m. How we can define? The mutual inductance between two coils, means M, is defined as the magnetic flux linked with the secondary, means equal to phi s, due to the flow of unit current in the primary. See, we have considered IP as 1, no? So unit current when passes through the primary, then this becomes equal to M. Okay, so this is the definition of mutual inductance, means M. Now from this we know ES means it is the induced EMF linked with the secondary, is equal to minus d phi s dt. Okay, Lenz's law. Then minus d dt, phi s means m ip, minus m comes out, we have d ip dt. So this is one equation. ES is equal to minus m d ip dt, this one. Okay. Now here we considered two coils. This is very important topic, this one. Mutual inductance of two long coaxial solenoid of equal length. So here we considered two coils like this. One is this one, the bigger one. Here it is, I have drawn it with a blue color, this one, bigger one, okay, and the smaller one, this one, another coil with red color, this one. Alright, they are coaxial because their axis is same. This is the axis passing through this line, okay. So this is the axis, and this axis is common for both the coils. Now here you can see that the name of this coil is S2 and the name of this coil is S1, means this one, the smaller one. Smaller one means its area is small, this one, smaller one, okay, but their lengths are same, L. Then suppose I1 current is passing through S1, that one we will consider for the first time. In the second case we will consider another current I2 passing through the coil S2, okay. So one by one we will do. So what we are finding here, actually we are finding a relation between mutual inductance of the first coil or S1 and the mutual inductance of the second coil. Means here two terms you will get. M12 means it is the mutual inductance of S1 with respect to S2. Another you will get M21, it is the mutual inductance of S2 with respect to S1. And we have to we are actually trying to show that this and this these are same, these two are same, equal, okay. So to prove that, let us start from here. Okay, so what I have written, let us consider two solenoids S1 and S2 having number of turns N1 and N2 respectively. The length of each solenoid is L, okay. Now number of turns per unit length of S1, number of turns per unit length of S1. S1 means which one? This one, this smaller one, okay, smaller area. N1 is equal to capital N1 by L. We know this one. This is number of turns per unit length. This is the total number of turns, okay. So total number of turns by length gives us this one. So this is for S1. For S2, what will happen? This will be N2, this will be N2 by L. Okay. Now one by one we are considering. Let when I1 is the current flowing through S1, then magnetic field inside S1 is which coil? The red color, this one, inside one. So when I1 current is flowing through it, what will be the field generated here? B1. We know for solenoid the expression for field is mu naught Ni. So mu naught N1 I1, because we are considering this coil I1. Current is flowing through the coil and that current is I1, okay. Then here we can write it like this also. Mu naught, in place of N1 we can write N1 by L also. Anyways, now flux linked with or flux in S2. See here, since current is flowing through S1, in this case S1 is the primary and S2 is the secondary, right? In this formula, phi S is the flux linked with the secondary. So here which one is the secondary? S2 is the secondary. So we are finding, suppose flux linked with S2 is equals to phi 2. That is equals to M12 into I1, just this formula only. M means here it is the mutual inductance of S1 with respect to S2, so M12, and I1 means it is the current flowing through S1, because here S1 is what? S1 is the primary, S2 is the secondary. Current always flows through the primary, okay, fine. So I hope this is clear, this part. Next, this phi 2 is the total flux. So we can write it in this way. Phi 2 is the total flux linked with the whole coil, which is equal to total number of turns in S2 into flux linked with each turn of S2. Suppose with each turn of S2 some flux is related. That flux, if you multiply with the total number of turns of S2, then we are going to get the total flux, which is phi 2. So this phi 2 can be written as this way. Okay, right hand side is remaining same. Now turns, total number of turns in S2, how much is that? S2 total number of turns means it is N2, no? This L will get multiplied with this N2 to get capital N2. So in place of this, total number of turn means it is N2L. Then this part is done. Then flux linked with each turn of S2. Okay, now see, flux linked with S2 is due to which current? Current flowing through S1, right? And field is created by which current? I1. So what will be the field here? B1. See, flux linked with S2, when we are writing, the general formula of flux is BA. Okay, magnetic field into area. But here this magnetic field is created by which coil? By S1, because current is flowing through S1. So that is why this B will be actually B1 and area I am writing A1. Clear? Okay. Now this area A1 means the smaller one, no? Which one? A1. A1 means I have taken this one, no? Right? So here we are finding the flux linked with which conductor or which inductor? This one. Flux linked with each turn of S2. Okay. But the thing is that if we are finding the flux linked with S2, why the area we have taken A1? B1 I think you have understood, because flux is, magnetic field is formed by which coil? By S1, because current is flowing through S1, which is I1 current. So that is why magnetic field will be B1, right? Why area is A1? Because see here, when current is flowing through S1, means this part, okay, current is flowing through this coil, inside one. Okay, so since it is a solenoid like thing, magnetic field will be only inside this solenoid, not outside the solenoid, because we know that outside solenoid magnetic field is 0. We got this concept in chapter 4. So the field lines will be confined only within the area of which coil? Of the first coil, because current is flowing through the first coil. Okay, understood? Above this means beyond this area, beyond the area of the first coil, means at this region, there, here and here, there will be no magnetic field, because magnetic field remain only inside the solenoid. Okay, so inside which solenoid it will be? The solenoid through which current is flowing, that is I1, S1. So what will be the area? A1. Okay, so I think this part is clear. So A1 we have written this side. Okay, then I1 get cancelled, we get this equation. This is given equation number 1. So we got an expression for M12. So M12 means what? It is the mutual inductance of S1 with respect to S2. Similarly we are proceeding like this. See, B1, then for the next one means suppose this time, okay, this is just a second, this one is I2, I2. Let I2 current is flowing through S2, then magnetic field inside S2 will be this. Just in the previous case it was this one, B1 equals to mu naught N1 I1. This time it will be N2 I2. This will be B2. Same steps. Okay, then flux in S1. In the previous case it was flux in S2. Now we are finding flux in S1. Okay, this will be phi 1. Previous case it was phi 2. M21, M12. This is I1, this is I2. Reverse everything. Okay, Now in place of S1, I mean for this one number of turns in S1, what we wrote in the previous case, N2L, it is N1L, B1 it is B2, but area is A1. This side also M12, M21, I1, I2. Only problem or only change is here, area again. Here, since, okay, though current is flowing through which coil? S2. Okay, current is flowing through, okay, one second, S2, yeah, current is flowing through this coil, bigger one, no? Wider one, this one, S2. So through this coil current is flowing, fine. Now flux is associated with which coil then? Smaller one, isn't it? Flux is associated with this coil. So since flux is associated with the smaller coil, which area we will consider? Area of the smaller coil. Can you follow? Because see, for this coil, when field will be produced, that field or that B2, that will be actually everywhere. Everywhere means inside S2. Everywhere inside S2 means this region. Here also there will be field line. Here also there will be field lines, field lines, field lines, field lines. Okay. But we are taking which coil? S1. We need how much flux is associated with S1. So why to take the outer region? S1 is only this part. So we will take the flux which is inside S1. So which area we will consider? Area of S1. How much is that? A1. I think this is clear. So that is why in the second case also area is A1. Okay. Then I2 get cancelled. What we have? M21 equal to this. Isn't it same with 1, equation 1? Same only, no? So equation 1 and equation 2, if we consider, we get M12 is equal to M21 equals to this value. Okay. Or this can be modified as mu naught will remain as it is. N1 means we can write capital N1 by L, N2 means capital N2 by L, A1 into L. To generalize this, in some cases in place of A1 you can write simply A. A stands for area of the smaller coil. Smaller in the sense thinner coil you can say. Okay. So this will be the equation again. Then the last topic of this chapter, that is coefficient of coupling. Okay, so coefficient of coupling is a constant which basically this is found or this is obtained when two coils are placed nearby. Suppose we have two coils of self inductances L1 and L2. Okay, they are placed nearby and thus there will be some mutual inductance also, which is M. Suppose if it is so, then this ratio M by root over L1 by root over L1 into L2, this one, this is called K or coefficient of coupling. It is unitless, right? Because this is also Henry. See, under root we are having Henry square, so Henry get cancelled, so it is a unitless quantity. The value of K, it lies between 0 and 1. When K is 1, the coupling of two coils are very tight, or we call that they are closely packed. If K equals to 0, they are loosely bound or loosely packed, and when K is 0, then M is also 0. The thing is like this. Suppose one coil is like this, another coil is there inside almost. So in this case they are closely coupled, closely packed. In that case the value of K will be around 1. Means whatever flux is linked with the first coil, the same amount of flux is linked with the second coil. So they are closely packed. Okay, tightly packed. So that's why the value of K will be almost 1. Now suppose if we have one coil here, then what? Obviously the field lines linked with this coil is not same with the field lines linked with this coil, so they are loosely packed. Okay, so that is the meaning of this one, coefficient of coupling. The value of K tells us how the coils are placed, whether they are closely packed or loosely packed. Okay, so that is the end of this chapter. Next video we will discuss the last chapter, that is alternating current.